Hi everyone. Today I will make my presentation about my research topic called Hilbert space. And because of the time limitation, I would only introduce the basic terms and what my research is about for the most topic of my research. So only for a very small part, I would focus on the proof. So let's get started. For my presentation. First, I would like to give an outline about my presentation. First, I will talk about the basic definition of Hilbert space and L2 Hilbert space. Next, I will talk about the Fourier series and convergence in norm of the series. Fourier series is a very important term for my presentation and for my research. So next, I'll talk about Bessel's inequality and Percival theorem. They are basically very important for proving the L2 convergence of Fourier series, which is the main goal of my research topic. So let's get started. From the Hilbert space, for this part, I'll talk about the definition of Hilbert space and L2 space. So for the Hilbert space, it is literally a special kind of inner product space with the norm defined by f equals square root of the inner product of two f's. So it's basically the same as other inner product. And this norm turns H into a complete metric space. So complete means that the causative sequence converge. I think if you are watching this video, you should be able to know what means complete and what means metric space. So I've not talked in detail here. So let's get to the L2 space. So what means L2 space? L2 space is literally called square integrable functions of space. So it is literally containing the square integrable functions. So it's from negative infinity to infinity, the integral of the square of the norm of ft. It is converged. And the inner product is defined as this one. The integral on the real number line for the ft times the conjugate of gt. Yeah, that's for Hilbert space and L2 space. So we want to introduce another term called L2 from 0 to 2 pi. So what means 0 to 2 pi? Instead of computing the integral on the entire real number line, in L2 from 0 to 2t, we compute the integral from 0 to 2 pi. Sorry, the 0 to 2 pi. So it is quite similar but different, right? And we want to talk about an orthonormal sequence in this L2 space. And it's called 1 over 2 pi times e to the ikx. So we want to literally prove this is a orthonormal sequence. So suppose fk equals our sequence. It's a term of a sequence. They have the inner product of two orthonormal sequence term is equal to this 1 over 2 pi times 0 to 2 pi e to the ix k minus m. So why is k minus m? We know that the inner product of two terms is equal to fk times the conjugate of fm's integral from 0 to 2 pi, so it's minus m. And then we convert this one to the triangular form. It is cosine kx minus m times x plus I sine k minus m times x. So, for the triangular term, it equals to 0 for the for an integral from 0 to 2 pi if kx minus m is some integer except 0. So if k not equals m, this term equals to 0. And if k equals m, then this is cosine 0 plus I sine 0. Then it is 1. And for the integral from 0 to 2 pi, then this integral equals 2 pi times 1 over 2 pi, and it's 1. So we know that this inner product equals to 0 when k dot equals to m, and 1 when k equals to m. So this means for all terms in the sequence is normal to each other, and the norm of each term is 1. So it is a orthonormal sequence. So this is, we define that this sequence is orthonormal. So now we want to define the Fourier series. The Fourier series of function f on interval 0 to 2 pi is listed below. It is literally a triangular form of the Fourier series. So it is similar as this term, but different. And we have the Fourier coefficient called AM and BM here. It is defined below. We don't have enough time to get through for it, but we should have an idea about what is Fourier series. So next, I want to talk about Bessel's inequality and Parseval's theorem. It is for the Bessel's inequality, it's saying that for a orthonormal sequence in an inner product V, for every f in V, we have the Fourier coefficients of f square as the square of the inner product of f and fk, which is the Fourier coefficient. The series from 1 to infinity is less than the norm of f, the square of norm of f. And the Parseval's theorem is stating if fk is complete, then the inner product V should be Hilbert space. Then the inequality of the above theorem becomes equality. So this one takes equality. And from Parseval's theorem, we could prove a very interesting conclusion that the series from 1 to infinity of all inverse of the perfect square equals to pi squared over 6. This is called Bessel's problem. So Parseval's theorem provide a solution of Bessel's theorem. So at last, we want to talk about L2 convergence of Fourier series. So we have defined what is Fourier series, and now we want to say what is L2 convergence. L2 convergence means for a orthonormal sequence Fn from an f become function in L to D. D means a interval on real number. We say that the sequence Fn converge in norm if square norm of Fn minus f when n to the infinity equals to 0. So this 2 means the sum of the square root of the sum of the square of each term in this Fn minus f. So we define L2 convergence of Fourier series, and for the time limitation, we will not get through the proof. It is quite difficult. It takes me about 3 or 4 days to fully understand this one. We currently don't have enough time, but we can say that Bessel's inequality, Parseval's theorem, and the orthonormal sequence we proved in this one plays a very important part of the L2 convergence proof. Okay, thank you for watching my video, and that's all for my presentation. Wish you all have a nice day. Thank you very much.